So hello, everybody. I'm Ting Liao from Stevens, and it's my great honor to be here today, particularly on the first day of May. I think it's a great way to celebrate this special day with all of you. And it's my talk on adaptive human AI systems, multimodal inference, and feedback for trust and cognitive float. So as Dr. Xu mentioned, I'm a mechanical engineer by training, and I conduct most of my work under this umbrella of engineering design and system engineering. So I approach concepts of data science and AI potentially from a very different perspective than both of you do here. So just to provide some context of my work, I will start with a brief overview of my research journey to position my research within this broader area. So this went all the way back to 2016. So when I began my research journey as a PhD student at Stanford, around that time, autonomy felt just around the corner. So even though it was just 10 years ago, it feels like maybe 2,000 years passed by. So besides being fascinated by the AI for geometric design or concept generation, I was driven by a simple question. So when should we trust an AI system? So at that time, autonomous driving was front page news, and we kind of staged edge case scenarios in a driving simulator to see when people rely on automation and when they intervene in safety critical situations. And since then, of course, AI has evolved rapidly, and I have worked with voice assistants that scaffold information retrieval, cognition, and now large language model that co-create in engineering design. But as AI advances, the research question I would love to answer remains. So pretty much, I would like to investigate this question. How do human users form trust in AI similarly or differently? We do kind of transform a lot of heuristics we use between interpersonal relationships to relationship between users and AIs. We want to know how much that remains, but how much they are updating. And as engineers and design researchers, how can we facilitate this process to achieve calibrated trust? We don't want people to over-rely on just AI recommendations, but we also want users to take advantage of those innovative technology. And how can we do that? How can we build an AI system that know when a human is struggling by leveraging potentially new data and learning models, and ultimately, how can we formulate new design principles and mental model in these areas? And to capture my kind of research landscape, so my core research area lays in this human AI collaboration loop. Currently, I focus on this human agent dyad, while I acknowledge they could be more complicated network with multiple human or multiple AI. So with all the we study this under different contexts and applications, including engineering design, where AI is a proactive collaborator, XR mixed reality-based training for high-stack environments, for example, high-frequency trading or manufacturing sites. You don't want to just get people out there before they are experienced. And in addition to that, we also do that for online learning, which is one of the important venues for higher education nowadays. And under those contexts, we try to, as a system engineer, we do manipulate different types of systems inputs for those applications and contexts. First of all, it was the task and environment, depending on the task complexity, difficulties, in the organizational structures, people can approach AI in different ways. In addition to that, user characteristics is important. Everybody has its own prior attitude towards strangers or new AI tools. Confidence levels, goal they're setting, can influence the overall interaction. And to the end, we also want to know how we can make better AIs using the known design attributes, including appearance, empathy, embodiments, et cetera, et cetera. And with that, the first task I've been working on is to see how people act, including how they behave and respond to AI suggestions and behavior. But beyond the behavioral level, we want to get to know more about the underlying mechanisms, including the cognitive parts. So we move on to the sensing and the inferring parts. So we collect multimodal data, including eye gaze, GSR, like interaction log, and also self-reported responses to infer latent cognitive states, including the cognitive loads, affect, meaning the emotions, and also the trust levels. So from observable behavior, we try to learn more latent states that potentially guide the future behavior, and also understand the real kind of the reasoning behind the scene. To the end, we want to loop it back to the system design. So the ultimate goal is to have adaptive system and with personalized interventions. We want to see how we should design the feedback and system behavior. So support is provided in the right content, the right timing, and with the right modality. Overall, we hope to bring better design performance. You probably gotta keep hearing this term design because I do work a lot within engineering design, but performance in general, like learning performance, engineering performance, we would like to enhance human performance entirely with the adaptive support. We don't want to overwhelm people with just tons of informations and explanations. And we want to make people trust at the appropriate level. So it's not the more the better. In most cases, we want to match human trust to the level of system capabilities. And at the science level, we want to have this theoretical framework for design and cognition with the multimodal influence model and principles for adaptive system design. All right, so that's hopefully gives a good overall picture for my research, and those 4 pillars also nicely map to 3 studies that I want to cover today. So let's start with the first one on the left, so the acting part, and the study 2 will pretty much talks about the sensing and inferring, and the study 3 will covers the inferring and adaptations. So the first study was motivated by this kind of prevailing trend of using AI in engineering design based on generative AI or like large language models. And speaking of trust, there are many research perspectives and methods related to trusting AI, including explainable AI for interpretability and assurance engineering for safety and reliability. And I believe, based on my background and my system thinking kind of mindset, that trusting AI research benefits from a system modeling construct that forms dynamic and design approach. So, because first of all, trust is a dynamic social technical construct. It is it forms dynamically with input and feedback. So it's like a conversational dialogue between user and AI, and users continuously assessing the performance of AI and adjusting its trust measurements. So it's not a static measure or a one-fits-all solution for different topics and contexts. Because this dynamic nature and dynamic and interactive nature, it can be modeled as a small system. And in addition, it is shaped holistically by system performance, including interface design, problem context, user emotions, and cognition. To model trust in AI systematically, we envision a modular kind of framework or test bed that let us very relevant design attributes and measure their impacts. Our effort here is trying to kind of isolate and assess the impact of individual design attributes so that we know which one should we kind of allocate more resources attention to. And in this case, we consider AI to play an proactive role, prompting and guiding design generations, which increasingly reflects real practice. So, yeah. So as the starting point, so I have been working on this for probably the past 3 years. So the landscape and my research strategy actually also evolves and being influenced by the involvement of AI itself. So at the starting point, we designed and developed the framework or test beds referred to as AI design assistant, ADA, progressively from a baseline Roberta model to an existing data set of 672 text-based concept description for sustainable design. To the Llama model, and then to a hybrid model with GPT API and Llama model. So this makes ADA more responsive in supporting creative ideation. And partially due to the nature of training data and domain-specific model, the design problems for the following study, or for this study, center around sustainability and text-based conceptual design. So it's the context is, or the environment is a little different from scraping text from Reddit or open source data. For a design problem, it's very hard or costly to get a nice, clean design data sets for a large size. And building upon this framework, ADA, as a proactive collaborator, presents this simple chatting interface on the left. It starts with greeting users and prompting design problems. And when a user inputs an idea, it goes through this flow chart. So it validates the scope. So if I ask you to design a sustainable washing machine, then your input needs to be relevant to washing machine. It cannot be about just sustainable building in general. So it first goes through this validation process. And then we have several predefined or commonly acknowledged metrics to assess the quality of the design inputs, including sustainability, novelty, and feasibility. So those are well defined in the domain of engineering design, and we want to assess if the input has a good quality and also a good creativity. And the combined results, so those models kind of performs in parallel, and the combined result is synthesized into a detailed critique and feedback for the users. So if you have done senior design, you may hear feedback from your instructor or the guest reviewer for the design, and it's kind of conducted in the same way. And leveraging ADA, this framework, we identified and tested 3 key attributes from a variety of design categories, so including aesthetic appearance, system performance, and agent behavior. So aesthetic appearance, or embodiment of the agents, seems pretty intuitive, but actually sets the stage for this AI user interactions. So sometimes, I mean, personally, I gave a name to my car because I feel emotionally attached to it. Then I might be more tolerant to its kind of, I don't know, it doesn't make mistakes, but I'm just more tolerant because I feel this emotional connection with them. So that's why we want to investigate into this aesthetic appearance. And in addition to that, performance is recognized as the dominant antecedent for trust in automation in general. The competence of the system, whether it makes errors, whether it gives false information, that influence the trust calibration and assessments a lot. Lastly, empathy and emotion recognition have been shown to influence interpersonal trust, and it has been emphasized in the design process. So that's something that robot may not be able to present, but designers do. So we incorporated, and for each of the 3 attributes, we incorporated 2 levels of each of them. For example, a humanoid avatar versus an abstract icon. And we used the factorial design to create 4 distinct design versions of combinations of those attributes level. So we chose this binary level just as a starting point. In the future work, we plan to have more granular levels or granular manipulations of those attributes. So yeah, so just briefly, we conducted a human subject experiment where each participant followed a looped structure. So for each of 4 design versions, versions means it has a different combinations of design attributes here. Participants were introduced to a sustainable design prompt, and they iterated on the design ideas with the AI generated feedback and inspirations. And looking and behaving differently. So they also filled a survey about their experience with that specific version before moving on to the next one. But they just loop this interaction to interact with all 4 versions in a randomized order. We collected data from 56 valid participants for an average study duration for around 61 minutes. We did observe group differences for self-reported attitude after interaction. So this color shows the groups or the versions, and those clusters shows effort, empathy, trust, enjoyment, helpfulness, and usefulness. So they showed a pretty similar trends overall. Um, and more interestingly, we found this consistent pattern for version 1, the one with all high attributes. So it consistently scored the highest in trust, enjoyment, perceived efforts, and usefulness. But version 4, so we have this U shape here. So the last bar represents vision 4, and that had abstract representation, non-detailed feedback, but empathetic responses. So and that scored second highest on this all these key metrics. So which one?
What's the Y?
Why? Oh, it's just a scale from 0 to 5. So it's so the those are self-reported attitudes after the interactions, and they reported their attitude on a scale, like a scale from 0 to 5. So the higher is better. I will put all those the scales here. But for each metric here, we have a full set of survey with subcontracts. So they get weighted and averaged to compute the self-reported perceived efforts of the AI system and etc. So so there is a big difference for the trust, which we are mostly interested in learning, and also perceived usefulness and perceived effort. Um, so and we also run some statistical analysis, including the mixed model, which shows that who um, like who we are or who they are and where they come from, including initial trusting attitudes and age, have a significant impact, as well as empathetic behavior on trust in the ADA system. So in the and we, this is so So again, a disclaimer. I'm from the design community, so we do those kind of conjoint analysis to see the ways or the trade off between all design attributes. So here we see the performance and the appearance are the most influential factors in driving user trust, and on top of it, because of the U shape you just saw. Recognizing emotions and building social connections may compensate for inferior performance of the AI. And this could be low-hanging fruit for a lot of designers because it doesn't necessarily cost them much computational power. But if you have an algorithm to see if people are frustrated during the conversation, then acknowledging that it could help to build the trust. But the question is, if the system doesn't perform very well, making people frustrated, should we still try to increase the level of trust in this relationship? So there is a dilemma out there. We collected a rich set of data and are currently exploring how participants' design performance and trust evolves at the micro level, meaning one kind of interaction of conversation, and also at the session level and at the group level. So here we have kind of a diverging or kind of symmetric pattern for the novelty and the feasibility scores. So this is a pretty simplified version of the analysis, but it's kind of interesting. As a hint, we observe this pattern over time at an aggregated level, class versions. So people or participants were prompted to iterate on their design ideas at least twice, and with AI feedback, novelty increased at the cost of feasibility. So they're I'm not exactly sure whether that was kind of an inherent bias of AI, which encouraged people to kind of brainstorm novel ideas or just perceived by users after being prompted for several times. And we are also diving deep into dynamic interactions with ADA for individuals while considering sentiment and creativity over time. So we envision the result will enable future adaptive systems and design guidelines for personalized support and coaching. And I'm as kind of a not an outsider, but like someone who works at an adjacent area of data science and machine learning. I would also want this talk to be kind of an initiation of following conversations. If you have interest or expertise in mining and understanding interaction log conversations in meaningful ways with sketches, then I would love to talk more about this topic. And from study one, leveraging ADA, we learned that trust and system design strongly influence how users interact with AI. But the interaction log only tells us what users do. What they write, what they sketch, but not why they do it. How much time do they use to? We roughly know how much time they use to review the AI suggestions and how much their next idea align with that critiques, but we don't know how they cognitive process those informations. So to build a system that are truly adaptive, we want to access the underlying cognitive states driving those behaviors and adoptions. So this motivates the next part of my work, where we move from observable interactions to multimodal inference of attention, cognitive flows, and uncertainty. And in this part, study two, we implemented this in context of online learning, as connecting people through virtual learning platforms has become an inevitable trend, with offering flexibility and convenience. On the other side, in most online learning environments, students need to self-regulate their attention, but a lot of them struggle to stay focused and allocate attention efficiently, leaving that space for distraction, disengagement, and wandering. So the particular metric or phenomena we focused first is called mind wandering. So this refers to shifting attention from task at hand to just self-generated irrelevant thoughts. And this could occupy up to 45% of online learning, which will significantly undermines the learning outcomes. And there has been research about revealing where learners locate their attention and accordingly design interventions whenever it's detected. Um, um, However, it has been pretty useful, and that's actually one of the target of my research in this study. But it's not quite enough to provide a comprehensive learning support framework, because mind wandering influenced by your prior knowledge or your familiarity with the topic. So if you're familiar with that topic already, you probably see it and just drift away, and which is pretty intuitive and acceptable. But if you're unfamiliar with the concept, or if it's too challenging, mentally challenging for you, you look at it and you just have this kind of fear or kind of obstacles that you need to overcome to fully understand the concept, and that's where the mind wandering and missing occurs. So at the end, I will mention that how we can move from content attention towards content understanding, but we'd like to tackle the content's attention first in the study. So we to capture this content allocation, or in other words, mind wandering, we utilized eye tracking based on this eye mind link or eye mind theory to reveal how learners collect visual information and process it cognitively. So where they look and how long and in what sequence indicates how they process information internally. So such insights have also enabled some interventions in the literature already, from traditional methods like pop-up quizzes, text recall, and screen flashes, like, oh, you're not paying attention, so I'm like blinking you to to re-engage students, to AI-powered avatar learning companion, which is a wonderful idea, I believe. However, for our second study, we found some of the intervention I just mentioned be quite distracting and sometimes disruptive, especially when learners are unmotivated. We observed a couple of students viewing online material, and a common feedback we got from them is they do not like to be interrupted during the learning sessions. If we tell them, "Oh, you seem to be distracted at this moment," the first reaction was mostly denying. They were like, "Oh, I'm thinking, I'm just processing the information." So, and this definitely varies from person to person. So it's hard to provide the intervention at the exact right moment. So we proposed and tested this delayed intervention process called the eye tracking based video reconstruction and replay to track and intervene in attention misallocation, but after the learning module. So, and this is, again, this is a delayed intervention, highlights potential knowledge and provides contextualized review. So this is probably too detailed about how we design the approach and triggering this or flag the missed material. But we mainly use fixation duration, pupil diameter, and and wandering time. So we set some thresholds and determine if any area of interest is missed or not sufficiently reviewed. So when the content is not fully learned, based on the framework, based on the threshold and the threshold, we determine if the content is not fully learned, the corresponding area of interest (AOIs) will be replayed and highlighted. Related AOIs will be replayed without being highlighted, and fully learned AOI will be stacked. So this is an example from the study. We did get some learning material from software engineering about DNS, and we consider each tag box as or diagram as an area of interest. So, and we also group them based on the content topic. So this two focus on one content, which is the definition of the DNS query, and the three bullet points and the diagrams illustrates how DNS query works and the order of the query. So they are kind of connected or grouped based on the content. So, and if two of them are not fully learned, for example, the first two, and they're replaced and highlighted with the right box around it. And those two, because they're grouped in the same cluster, they will also be displayed, even though they are considered fully reviewed. And the top two are mosaic, so indicating that learners do not have to spend extra time on them. So again, I forgot to say that I'm an experimentalist, so I do most human subject experiments. So we again conducted an experiment to evaluate our framework and its effectiveness on learning improvement compared to a self-paced replay. So to examine whether, and we also examined whether the improvements were particularly driven by over reconstruction and review mechanism, because it's possible to just view it for the second time and just fix the misunderstanding and become better. So we want to see where they improved and where they review in the second time. So this was a controlled study. So we have just in case you will conduct this kind of experiment in the future, this is the monitor. We have this Toby Pro Fusion, and we calibrate the participants and in this sitting position. So we have the pre-survey learning video, the quiz, and the replay based how on how their gaze pattern in the learning video, and then we have a quiz too to assess the learning improvement. So every participant's replayed video is personalized while they are doing quiz one. Of course, through automatic algorithm, but everyone will see a different replayed video. Um, so briefly, we had 41 participants, and we also collected their English proficiency level, and we categorized them into high and medium proficiency. We collect their familiarity with the topic, because some of them may already learn this in their courses. So. So this is histograms of the prior knowledge or familiarity of the topic based on groups, so experimental versus control, and they were pretty much homogeneous, and we didn't test for any significant difference either. And we did not observe an impact universally, but for the learners with lower familiarity with the knowledge points, the EVR had a significant positive impact on the score difference between the second and the third score. So we used the score from the second to and subtract by the score of the first. So our hypothesis that EVR leads to a higher positive score difference than the self-review is partially supported. So and we also like to know if as I said, to just test if the system is valid or perform as we expected. We highlighted to see if we highlighted the right AOIs for participants, and if that led to the improvement. So we test this hypothesis too, and we calculate the rate of AOIs being highlighted during the replay, and we found that replaying more AOIs that are related to incorrect quiz responses led to greater score improvement. So this hypothesis is also supported. So we also did analysis on the self-reported skills. So we found, I think, most importantly, we found the eye tracker usefulness and the nervousness had significant negative impact on the first quiz scores. So potentially those devices and this not very natural sitting gestures made them not being able to focus so much on the first quiz. Yeah. So we had we had this conclusion that EVR can significantly improve learning outcomes compared to the self review, especially those who are unfamiliar with the concept. And I think this gives a really good use case scenarios, because those who are less familiar with the concept needs greater support, and this can actually fill the gaps for those students. And of course, just to acknowledge the limitation, for every human subject study, the sample size is always a concern, and the mind wandering feedback could be influenced by familiarity bias. I just so as I said at the beginning of this study too, in addition to mind wandering, we were also trying to detect other important metrics, including confidence and hesitation. So hesitation is critical in this case because it captures a cognitive uncertainty during decision making, and it's even when you got the answers right. and it will help to reveal hidden or fragile understanding that accuracy alone cannot detect. So, so as a process level signal, hesitation pretty much complements attention and confidence, and allow us to have a more precise identification of where learners need to support. Um, so this is ongoing studies. I will show what we have done so far. So we in the second, so in the future exploration, we have a similar structure and we had the same hardware configuration, but instead of having two quizzes, we only have one. And after each question, we also ask participants to self-report their confidence and I had confidence for twice. Self-reported confidence and self-reported hesitation. And after the whole session ended, there were also reported the mind wanderings. So those serve as labels for our like inference models. Um, so so similarly, we had 35 participants, and we also asked for their English proficiency and familiarity level. So, so this is our preliminary results for the classification model for regarding the hesitation detections. So this is kind of the we started with this pretty kind of basic random forest and hyperparameter tuning, and then this like plus validations, and it achieves an accuracy of 72%. But this was based on the whole data sets here. So the 35 participants data sets. And because it's just binary classification, we have this confusion metrics here. So I won't go into details of this because this is subject to change. We are still trying different models and try to see if we can improve it or using different layers of features to make this more accurate. And again, if you have interest or have any suggestions for how we should proceed with eye tracking data for hesitation detection or confidence detection, I'm more than happy to talk more about it. But just a summary. So we did invent or did propose and test this delayed video reconstruction and replay. And we are trying to do this hesitation and mind wandering predictions so that we can understand how information and decisions are processed internally at our cognitive level using the eye tracking data. And of course, for the final, if you recall the diagrams I showed you, as the last step, we really want to connect the inferring parts to the system adaptations. So from this work, we learned that eye tracking provides a meaningful signal to detect how learners engage with content. But this also raises two key questions. First, how can we capture dynamic cognitive state? Because currently, for this study, we process eye tracking signal after they finish reviewing the learning material. But it can evolve during the interactions. And second, how can we design systems that adapt in real time? So, it depends. Even though I said that some participants in our pilot study said they didn't want to be interrupted, I think there is still value to provide dynamic, at least monitoring and potential for interventions. So that's why we move on to this third study. And we intentionally tried different environments and contexts and signals. So in all my three studies, we use very different signals and applications. So this one is AR, and that integrates real-world So we use HoloLenses too. Unfortunately, I don't think it's still supported by Microsoft, but we I think we use it and it worked fine. So the AI pretty much overlays virtual content onto real worlds and requiring simultaneous processing and potentially increase cognitive loads, stress, and difficulties of engagements. So we and traditionally cognitive load have been measured using subjective methods like questionnaires. If you have done any work using this survey, this I think this has been there for like 50 years, and it has been like the golden standard. And even though no one likes it, everybody just keeps using that. Uh, and but of course, there are other methods for monitoring cognitive loads using physiological data. But here we are trying to address the gaps, including it's hard to measure it real time and as well as in a cumulative manner. In addition to that, we also want to incorporate this assessments, real-time assessments, into dynamic task conditions in AR. So just to give you some idea about the signal we capture, we do galvanic scene response. So it's we do it for partially because it's a relatively simple signal compared to eye tracking and EEG. So it's easier for us to implement this real-time feature. If it's too much data, it will be certain kind of transmitting latency. Um, and recent progress in those signals or sensing technology has been approved or has been tested to show a, show good results or show it as a good indicator of cognitive load. So that's why we decided to go with this as the starting point. And this signal pretty much, so this is a single channel signal. So it plays the kind of the electrode on your finger or on inside of your wrist, and it detects kind of the skin conductance based on your arousal. So if you get excited, then you're about to kind of sweat, and it senses the skin conductance. Because it's a single, so this is the example of the GSR signal. So this is what we can get from real time, um, and 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 there is a metric related to this based on literature, which is SCR. The SCR, standard SCR capture kind of the fluctuations or how much it rises within a unit period of time. So if it rises for more than, I think, 50% from the previous time period, then it's recorded as one. So this is the raw signal, or GSR, and SCR is kind of the count of the rising. But since it's a count, we don't think it's an accurate measure in a continuous task. So we propose this new metric for cognitive load for real-time interaction, which is a CSCR, and the C stands for cumulative. So here is a comparison between the SCR, standard SCR, and the CSCR. The red dashed line shows just the cumulative nature of cognitive loads. Because if you are engaged within a super demanding task, maybe for 15 minutes, for example, if you're taking a final exam, and even though maybe answering each question is not very exhausting, but if you keep doing that for 15 minutes or 2 hours, it can be a nightmare. And we do believe this cognitive load or mental stress accumulates over time. So again, fun experiments. So we ran this maze task in in augmented reality environments. So this is what we got from just what we got screenshots, which is not very nice. It's distorted somehow from the AR to the laptop screen. So there are two different types of maze. One is rather simple. One is a little bit more complicated with a trick here. And you can use your hand or actually gaze to control this the cubic from the starting point to the end. Um, it's not as easy as you may think. If you're not familiar with AR, especially for the eye gazing one, you have to stare at it to select the cubic and then move through the path. So, and we do this in a randomized order, so that after each task, for their cognitive level, and they got some time to rest. And during the whole time, they wore this sensors to track their cognitive loads or GSR as a proxy of cognitive loads in real time. So this is the trick I mentioned. So there's a narrow path here. In VR, it's a little bit hard to see, but it can get stuck if you try to go from this route. And when it gets close, you get some participants will get some hint about this is too narrow for it to pass. So you have to go through another route. So this intentional design to increase their cognitive load, so that's not too easy for everybody. And the system is designed to monitor CSCR level continuously. So we have the algorithm calculated the cumulative cognitive loads throughout the sessions. And when it crosses the predefined thresholds, a rest break is automatically triggered to help participants recover and maintain optimum performance. So this is kind of the interface with, so we have a color indicator. We have this message message to show how much stress they have and how much time they use for this task. So currently we have this defined threshold for triggering the break, but how many triggers was personalized because it all got calibrated based on their own GSR data. So of course they can chose to exit the break. And while they got prompts to take a break, they can also see their stress levels and how much time they got for recovering. So we collected different types of data. We have HoloLenses to collect the eye tracking data. We have the GSR running on the background, and we also have the questionnaires, including the NASA TRX and also the post-interaction surveys. So briefly, we was able to evaluate the effectiveness of CICR as a metric for cognitive load. We compare it against the golden standard NASA TRX, and it shows a pretty strong correlation between CICR and cognitive load, and it actually is more closely related than the existing scale, which is SCR. And this one doesn't have the cumulative nature of cognitive load. So our first hypothesis is pretty much supported. And we also tested if the intervention actually helped people to reduce the accumulated stress or accumulated cognitive load and improve mental state. Yes, and the results shows yes. The CSR with the intervention on average is lower than CSR without the intervention, excluding the resting periods. Of course, with the suggested rest period, the overall length of the study is longer. And the task efficiency is actually lower than before. So that means for this type of task with this level of difficulties, most people can still just carry through, even though we think they experience a relatively high level of cognitive load or stress. So so just to summarize, we successfully validated this as a sensitive and effective metric for cognitive load. So it can provide this continuous signal for us for future intervention and system adaptation. And adaptive feedback reduces the cumulative cognitive loads, providing one feasible options for system intervention. Um, so the resting, like the disruption, was actually aligns with the previous insights we got from the pilot study. The resting periods positively impacts cognitive load, but it really limits the task efficiency, and still a lot of participants found it to be pretty interruptive. Some of them decided to just accelerate the rest and continue the task, even though we didn't ask them to compete on the shortest completion time. They still did. Just I think briefly, I'm probably running out of time here. Oh, so okay. Okay. Yeah. Okay. Summary. It's a good metric. If you um, we tested different signals and we see the correlation with the current golden standard, and we found it to be a useful uh, uh, value for future intervention. So I will actually bring back to this kind of diagram of my research. Hopefully you have a better idea how this really, study fits in this diagram. And also, oh, I don't know, I have something on overlay text. So trust is something I have been passionate about and working on for the past maybe 10 years since I was a PhD. My work has been supported by NSF ELI and NSF Career. The career starts in September, and I very much look forward to that project. In that project, I will integrate all the signals that I mentioned in this talk into fusion models to see if we can have a meaningful prediction of latent state, and having a closed loop adaptive system is definitely one of the goals of my project, and ultimately I want to enhance design outcomes. And all right, so this is all I have, and I feel like I used all the time for questions as well. But as I said, my research is uh, close, but not exactly where the primary focus of this department. But I do see a potential for collaboration for us knowledge to complement each other. So if you have ideas about mining multimodal data or learning human patterns using innovative models, I'm more than happy to have more conversations. If you want to know more about the publications, I didn't put them out there, but I'm more than happy to talk about them too. Right, thank you very much.